Okay, good morning everybody. Hello, we will continue for around 20 minutes the lecture, and then we will talk about the directions for the short quiz. Okay? Okay. Okay, so last time we were talking about the effect of the source to body voltage on the threshold voltage. And we said that finding the threshold voltage is the first step for us to continue to see if the device is on or off. And beyond this, we will then, if it is on, use the specific current model or current equations to estimate the operation of the transistor. So we said that for the NMOS device, if VSB is positive, what we will have is that VT will increase, and in a similar fashion for the PMOS device, if VSB is negative, yani if VS is less than VDD, then the magnitude of VT P is going to increase. And the equation for the PMOS device, we said that it is VT0, which is when VSB is equal to 0, plus some body effect coefficient multiplied by the difference between those two terms. One of them takes VSB into consideration. And so in this last example that we have here, we try to calculate VT for the PMOS, knowing that the PMOS voltage is minus 0.4, yani VT0 is equal to minus 0.4, and knowing that the body effect coefficient is minus 0.4, so gamma equals to minus 0.4, and the threshold voltage, we want to find it when VSB is minus 2.5, and they tell me that 2 phi f is equal to 0.6. So technically, if we want to write the equation, we will say that VT is equal to VT0, which is minus 0.4, plus gamma, which is minus 0.4, multiplied by the square root of minus 2 phi f plus VSB, and the absolute value of minus 2 phi f plus VSB. Okay, so if we go back to the equation here, this is minus 2 phi f plus VSB. So this is minus 2 phi f, this is 2 phi f, this means minus 2 phi f is minus 0.6. Okay, and VSB plus VSB is minus 2.5, and then here this is minus 0.6, and we end up, if we plug in this information, which is VT0 plus gamma into the square root of absolute value minus 2 phi f plus VSB, we end up finding out that the value of the VT becomes minus 0.79. So we started with a VTP equal minus 0.4, and we ended up with a VTP equal minus 0.79, so it almost doubled in absolute value. Okay, so it almost doubled in absolute value. Okay, so this concludes our analysis on the effect on the threshold voltage, and we will now shift or move to another set of slides اللي هن part 2. And in part 2 for the current equations, we will be looking at the basic model. يعني رح نرجع نعمل revisiting quickly for the regions of operation, and we will then look at the long channel model and the short channel model. So we said last time that in the transistor, the current is function of VDS and VGS, and VT mainly is function of VSB. So VT is a function of VSB, so the body will indirectly be included in this equation if there is any body effect. And we said that if the device length is greater than 1 micrometer, we will have the long channel equations. But for the newer technologies where L is shrinking and becoming much smaller than 1 micrometer, the transistors are becoming weaker and we have some short channel effects. And this comes from due to the fact that the electron velocity saturates. What does it mean that the electron velocity saturates? We said that my transistor, I will have N plus, and here I will have the gate node. If a channel exists because VGS is greater than VT, and if I apply a positive voltage here and a negative voltage here or a ground, the electron is going to be swept to the positive terminal. The distance which the electron crosses, and we will talk about that later, in the transistor is really the channel length. So this is the distance which it crosses, okay? And the electric field, if I'm applying a voltage V here, the electric field is really V over L, okay? And the velocity of the electron is equal to mu times E. So it's proportional to the electric field. So what's happening here is as L is decreasing to the nanometer, the electric field is increasing for the same operating voltage and the velocity is increasing. Now the velocity cannot keep increasing indefinitely. يعني أنا as I am moving from L equal 1 micron to L equal 10 nanometer, I have dropped by 100 times. Can I increase the velocity, keep increasing the velocity depending on the voltage 100 times? No, because we as humans have a limit to our speed, the car has a limit to its speed, and in a similar fashion, the electrons will have a saturating velocity when the dimensions shrink, and this is what we call by short channel effects when we are talking about the electron velocity saturation. And we will implement a simplified unified model that takes this into consideration, that adds one condition to the long channel model. So this is what our target is. Of course, there are other nonlinear effects that kick in into this formula here. Okay, so let us now move to the next slide. So there are some parameters that we need to look into, and those parameters are that we need to take into consideration. First, we know that if I have two parallel plates, okay, and I have a material which is an insulator between them, okay, the thickness of this insulator is D, and the area of this parallel plate is A, then the capacitance that is formed by this parallel plate is equal to C, is equal to epsilon of the dielectric times A over D. Okay, so هيدا it's a general capacitor formula. One thing that we need to note in the MOSFET is that the MOSFET, given that this is the metal gate, has some silicon dioxide here, and the thickness of the silicon dioxide, the value is Tox, okay? And if I want to measure the capacitance at the gate, basically that is responsible for the charge accumulation in the channel. لأنه the capacitor will, what does the capacitor have? It results in charge accumulation, right? So in a similar fashion, the capacitor is going to be responsible if Vg is positive to charge accumulation. One surface will be the channel, okay? And so because Q is equal to C times V, we will want to know what C is, and so we are going to define a term which is called Cox, which is the capacitance per unit area Okay, and I don't know the area, but I'm going to define it in terms of the parameter epsilon ox over T ox. يعني الكاباسيتور it has a thickness T ox D, and the property of the material E هي epsilon ox here. I will have here epsilon ox. So I'm determining the first portion of the equation because it is always constant for all devices, for all transistors that have the same Tox. So we define this capacitance Cox equal epsilon ox over Tox. Okay? So let
Professor,
us, yes, yeah, I'm going to, go ahead.
هيدا this capacitance, do you consider it a parasitic effect? يعني is it not desirable ولا what do you
No,
consider?
it is
Is
a
it wrong to think of it as
desirable,
parasitic?
well, it is parasitic for delay, but at the same time, it is the reason why we have charge accumulation in the channel, right? And the gate controls the channel via this field across the capacitance, right? So I'm going now to draw for you a very basic sketch, and this sketch is going to show me a three-dimensional sketch of the transistor. And here we are going to talk about, this is the gate. So underneath the gate, there is this oxide layer, right? So the gate is a layer that has like connected on top of this oxide layer. The thickness of this oxide layer, we agreed that it is the thickness of this oxide layer is really Tox. Okay, above this oxide layer, I have the gate, and under it, I really have the channel is residing, right? Because then the channel is interfaced to the body, which is grounded. Okay, and what happens here is I have a charge accumulation, so the channel will have all the electron charge, and the gate will have all the positive charge coming from the gate voltage. Okay, if I want for a specific transistor to find what is this resulting capacitor, then as we said, C is going to be equal to epsilon ox over Tox times the area. And the area of this surface here, okay, this surface here, this is, we said, the width of the transistor, and this is the length of the channel, right? So this is W here, and this is L, so this is W over L, times L, pardon me, this is W times L, is the area, and this epsilon ox over T ox is the C ox that we just, sorry, W times L, that we just calculated before. So now what we care for is to define a unified value, which comes, because the T ox is independent of L and W for all the transistors, T ox will be constant, and epsilon ox is property of material. We define this as the capacitance per unit area. Okay, and then for a specific transistor, we multiply it by W times I. Okay, so if we go back to the previous slide, we will define Cox. Now we want to know how much charge I have, because depending on how much charge I have in the channel, this charge is going to move and it will be responsible for my current. So Q equal to C times V. And V is basically the voltage that is the overdrive voltage that is applied through the gate. Okay, so this is the charge induced is C times V, and this V is coming from the overdrive. Okay, now on a different angle, this charge that is somehow created by the effect of how much Vg is greater than Vt is going to move in my transistor if this was the source and this was the drain. Okay, and the force that is moving those electrons in this direction is really due to the electric field created by the drain through the source. Yani, once I have the channel, once the channel is formed, then I apply the V drain voltage, and I apply the ground here at the source. Okay, so this is the source, and the electrons are going to move based on the voltage VDS. يعني drain to source voltage will attract them or create their motion or mobility. So the mobility or the carrier velocity of the electrons is determined by mu E, where E is the electric field which is due to VDS over L. Okay, فإذا we are starting to see the picture how the current is forming. It is forming via the interaction. First, the channel forms from the gate voltage, and the VDS forms from the electric field due to VDS causes the carriers to start to move and create the current. Okay, هدول two quantities are important. The second quantities that you are familiar with from before is that K prime, which is the transconductance parameter, is mu times Cox. And if I want to take the dimensions of the transistor, then I define a parameter K, which is equal to K prime times W over L. Okay, K prime times W over L. Anybody has any questions?
Professor?
Yes.
Can you please repeat how we got the electric field and know the formula?
Yes. So if we look here, the electric field, when I am applying across the channel whose length is, what is the length of the channel? L, right? So first I have the carriers, they formed from the gate voltage, right? And then I apply a voltage V across a material of length L. What is the electric field? If I apply an electric field,
V over L, yeah.
L, V over L, exactly. So this distance is L, and I'm applying V here. I get a field which is equal to V over L. But the voltage here happens to be applied from the drain to the source, so I'm horizontally, right? And the distance between the drain and the source is the channel length L. Okay?
Yes, okay.
Okay, great.
Thank you.
Thank you very much. So, بس هيك the last 1 or 2 minutes, basically, what we talked about last time is that if my gate voltage is less than VT, the substrate will remain, will have holes. So هون عندي الانسوليتر، هيدي الجيت وهيدي السبستريت. If I apply VGS equal VT هون عم يعطيني strict definition, I would have fully depleted my region from holes. And if I start to have an overdrive by applying a gate voltage VGS greater than VT, then charge will, negative charge will be inversion. This will be what we call inversion, will build in the channel region. And the amount of inversion charge is proportional to the capacitance, اللي هو Cox ضرب W ضرب L, and it is also proportional to the overdrive voltage, which is VGS minus VT. So بلشنا نطلع قد ايه عندي charge. Okay, next time we will talk to you over how we derive the current. Okay, so حنجي نقول إنه الكرنت I هو dq by dt. Okay, really, if I want to look at the time who is really what the distance over the velocity. The distance which it crosses is L, and the velocity is mu times E, and E is nothing but VDS over L. So حليت الفاكتور تاعون التايم. Next time we will derive it slowly. And then the charge is really C, اللي هي Cox times W times L مضروبة بالoverdrive voltage. Okay, so you can start to see that if I plug in all of these, I will start to see some form of the linear equation, linear long channel current equation that we have. And from this, we explain to you that this is how the linear current equation builds. And then we explain to you what are the different regions and stuff like that. Okay, so